Okay, let's finish up on the test review for related rates. Number 5, a sphere of diameter 4 inches is inside a cylinder. So we have a sphere that's inside a cylinder, and that cylinder has a radius of 12 inches and a constant height of 8 inches. How fast is the volume between the sphere and the cylinder changing if the diameter of the sphere is increasing at a rate of 12 inches per minute and the radius of the cylinder is decreasing at a rate of 4 inches per minute? So just to think about how we can set this up, there's going to be the volume that is, we're trying to figure out the rate of change of the volume that sits between the cylinder and the sphere. So we can just set up that formula. The volume that's between the cylinder and the sphere is simply the volume of the cylinder minus the volume of the sphere. So if this is our starting formula, we can simply find the derivative of each v. So dv over dt of b, of the volume in between, is equal to the rate of change of the cylinder minus the rate of change of the volume of the sphere. So this is going to be what we're trying to get after. If we can find the rate of change of the volume of the cylinder, and then if we can find the rate of change of the volume of the sphere, then we can just simply subtract those two to find the rate of change of what sits between those two figures. Okay, so let's start off with the sphere. The sphere is v is equal to 4/3 pi r cubed. Let's see what we have. We know the radius of the sphere is 2 inches because the diameter is 4 inches, so we want to use radius. dr dt, we see that the diameter of the sphere is increasing at a rate of 2 inches per minute. So if the diameter is increasing at a rate 2 inches per minute, we know the radius must be half of that. So the radius is increasing at a rate of 1 inch per minute. And so we have enough information now to find dv dt for the sphere. So we find dv dt going through power rule. We get 4 pi r squared dr dt. Don't forget this portion. dv dt is equal to 4 pi r. R is 2, so 2 squared times dr dt, which is 1. Multiply this through, we get 16 pi inches, cubic inches per minute. And it makes sense that dv dt is positive because dr dt is increasing, the radius is increasing, so we expect that the volume to be increasing as well. Hey, let's find the volume for the cylinder. We know they tell us that the height is constant. So if it's constant, that means never changing. We can just go ahead and replace that in for h because there's no need to hold on to that variable if we know that it's just going to remain the same value all the way throughout. So replace h with 8. We know r is 12 inches, but that's just a moment in time. So we don't want to replace r in for 12 or 12 in for r because radius is going to be changing for this particular cylinder. Normally it doesn't, but in this case our cylinder is increasing sideways while the heights are remaining constant. So they tell us dr dt is negative 4 inches per minute. We see that because the rate says that the radius of the cylinder is decreasing at a rate of 4 inches per minute. Okay. And so we can find the volume by replacing h with 8. So we get pi r squared 8 pi r squared. So now we're ready to find the derivative. We haven't found the derivative yet. So v becomes dv dt. 8 pi r squared becomes 16 pi r dr dt. Replace the r with 12. Replace dr dt with negative 4. And we simplify this to give us negative 768 pi cubic inches per minute. So we have dv dt for the cylinder. We have dv dt for the sphere. We can simply subtract those two, and that'll get us the rate of change of the volume of this region that sits between what's inside the cylinder but outside the sphere. Okay, so it's negative 784 pi cubic inches per minute. Okay, last one here, dealing with similar triangles, dealing with Pythagorean theorem. A boat is pulled toward a dock by a rope. So here's a rope represented by Z. From the bow through a ring on the dock that is 6 feet above the bow. So The y value represents the distance from the water to the dock. And the rope is being hauled in at a rate of 2 feet per second, so we know dz dt is going to be getting smaller. That z is getting smaller, the hypotenuse is getting smaller because that boat is moving in closer and that rope is getting pulled in. So dz dt is negative 2 feet per second. Our y is remaining constant at 6. Z at this moment in time, we're looking at this part A now. How fast is the boat approaching the dock when 10 foot of rope are out? So z is equal to 10. How fast is the boat approaching? So that's dx dt. So the equation that relates all the variables together is Pythagorean theorem. We find the derivative, and then we replace x, y, and z with 8, 10, and 0. Also, 0 is the for dy dt because there's no that rate between the water and the dock is not going to be changing. And to find the x value, we go through Pythagorean theorem. So now we have everything that we need to plug in. 16 dx dt, this goes to 0, is equal to negative 40. Solve for dx dt, we get negative 2.5 feet per second. Part B, at what rate is the area of the triangle changing? So the area of a triangle is 1/2 base times height. My base is x, my height is y, so 1/2 x times y. If we find the derivative, we're going to have to use the product rule because x and y are both variables and they're being multiplied together. So f prime g plus f times g prime. Replace y with 16, dx dt we just found, negative 2.5, and x with 8, and dy dt is 0. So all that cancels out, leaving us with just negative 7.5 square feet per second. So area is square feet with respect to time, so per second.